Hello everybody. Today I am going to give a presentation on the topics ray optics. So this presentation I am doing as part of my coursework in IIT Madras. So here we are mainly talking about the course is mainly about introduction to photonics. So the photonics is related to the light rays and the application of that in the electronics side actually. So here mainly we will start with the ray optics, then we will move to the wave optics, and then to electromagnetic optics, then quantum optics, and at the end we will talk a little bit about the nonlinear optics. So here the introduction to photonics class, we were talking about the different categories of the optics. So the initial one is the ray optics. So here we are considering the light waves as straight lines. So Sir Isaac Newton and Pierre de Fermat were the most famous scientists who were working in this area, and they have mainly Fermat initiated the principle that light travels along the path of least time, and the Isaac Newton set forth a theory of optics in which the light emission consists of the collection of corpuscles that propagate rectilinearly. So mainly in this ray optics, the light waves are considered as something which is moving in straight lines. So the light waves will propagate through and around objects whose dimensions are much greater than the wavelength of the light. So that is the characteristics of ray optics. So here the behavior of the rays are mainly explained with respect to some geometrical rules, and they are described by the rays, and the rays are obeying some geometrical rules. This is the simplest theory of light, and the light wave travels in straight lines, and here each ray is associated with a location and a position of the location and the direction actually. So here mainly we are dealing with the location or the position of the light rays. So this ray optics will help us to understand the image formation, guidance of light through the mediums like optical fiber, etc. So there are mainly two important laws in the ray optics. One is the law of reflection. So the law of reflection is a principle or rule that governs the phenomenon of reflection of light. So the law of reflection states that a light ray will reflect off a surface at the same angle that it hit it when it comes into contact with it. So here, in a nutshell, we can say that the angle of incidence is equal to the angle of reflection. That is, the reflected angle is equal to incident angle. So that is what the law of reflection says. So here we can see an incident ray is incidenting on a mirror, and with respect to the normal, it is making an angle of I, and that is called the angle of incidence, and the reflected ray which makes an angle of R, which is called the angle of reflection. So those two will be the same always. So the incident ray is the ray of light that falls on the reflecting surface, and the reflected ray is the ray which is supposed to be reflected back after striking the reflecting surface, and the angle of incidence is the angle formed by the incident ray with respect to the normal, and the angle of reflection is the angle which is made by the reflected ray with respect to the normal, and the normal is a straight line which is perpendicular to the reflecting surface that acts as a separation between the plane of incidence and the plane of reflection. The second law is the law of refraction. It is also called as Snell's law. So here it is mainly dealing with the reflection or refraction which is occurring at the boundary between two different medias. So at the boundary between the two medias, and the two different medias are differentiated by two different refractive indices. So here we are saying N1 and N2 are taken of the refractive indexes of the two mediums. So then the ray will be split into two. One is called reflected ray and another one is called the refracted or the transmitted ray. So the law of reflection explains the relationship between the angle of incidence, the angle of refraction and the refractive indices of the two medium. So that is what is given in the right side. N1 sin theta 1 is equal to N2 sin theta 2. So here N1 is the refractive index of the first medium, that is the medium from which the incident ray is coming. Theta 1 is the angle of incidence and N2 is the second medium's refractive index. Theta 2 is the angle of refraction. So N1 sin theta 1 is equal to N2 sin theta 2. That is the Snell's law. So here it is also showing an example of law of refraction. So whenever there is a, here on the right side, that red material is the gelatin, and from the air the light is passing through the gelatin, and at the outside it is also passing through the air. So at that time the light will experience a slight bending or the refraction. So now we will talk about some simple optical components. The first one is the planar mirror. Here the planar mirror reflects the rays such that it is originating from a point P1. That means the rays are coming from a point P1 and that will incident on the mirror, and from the mirror it will get reflected such that the rays are coming out from a different point which is behind the mirror. So that point will be also having a same distance as that of P1 from the mirror. So that is called the image of the object, or the whatever we are placing at the P1, it will be having an image at P2. In the case of paraboloidal mirrors, it is having a property called focusing property. So all the incident rays which are coming parallel to its axis will focus onto a single point called the focal point. So it is mainly used in the antenna, receiving antennas or radar, etc. In the elliptical mirror, it is having another property, that is whenever we are having, it is having two foci. P1 and P2 are the two foci. So an elliptical mirror reflects all the rays emitted from one of its foci, example P1, and images them onto the other foci. So it is called the imaging property. So the paraboloidal mirror is having the focusing property, elliptical mirror is having the imaging property. So it is mainly used in the bathroom mirrors and decorative wall mirrors, etc. So it is also used to couple the light to the optical fiber cable. Then spherical mirrors are also there, which is easy to fabricate compared to the other two mirrors, and it is having neither the focusing property nor the imaging property as that of the other mirrors which we have discussed. So it is mainly used in the traffic systems or in the case of medical aids, such that then this will be using that to get a clear vision. Then in the ray optics, a ray is always characterized by its position and its angle with respect to the optical axis. So these two variables are altered when the ray travels through an optical system. So here it is represented by two linear algebraic equations, and that equation will lead us to a matrix called ray transfer matrix. So here in the picture it is given the red arrow is the light ray actually. So with respect to the parallel optical axis, it is having an angle theta, and from the optical axis it is at a height of y distance. So this y and theta are the two variables which are characterizing the ray in the case of ray optics. So here we are having an input y1 theta 1. The input ray is characterized by y1 and theta 1. The output ray is characterized by y2 and theta 2. And these two are combined or related by an equation 1 and 2 is given. Y2 is equal to a y1 plus b theta 1. Theta 2 is equal to c y1 plus d theta 1. So that can be written as a matrix A, B, C, D. So that is called the ray transfer matrix. Now we will come to the basics of fiber optics. So fiber optics is a cylindrical waveguide and it is having mainly two different parts actually. One is core and another one is the cladding. Core is having a higher refractive index compared to the cladding. So the light rays, when it is entering into the medium, it will incident on the core cladding boundary at angles greater than the critical angle. And in that condition, it will undergo a total internal reflection and the light will be guided through the core without refraction into the cladding. So usually in the optical fiber, we are getting a loss of 0.2 dB per kilometer. It is a very less loss actually. It is a low loss medium. So the total internal reflection is the main concept in the case of optical fiber communication. So the full reflection of a light ray at the boundary of two media when the beam is incident from the higher refractive index medium is called the total internal reflection. So here in the figure it is giving A is the incident ray, B is the reflected ray. So whenever and I is the angle of incidence. When this angle of incidence is greater than the critical angle, at that time the wave will be reflected back into the same medium. So the critical angle is the angle of incidence at which the refracted angle will be equal to 90 degree. That is what is shown in the second figure actually. So here if we apply the Snell's law, we can see that n1 by n2 is equal to sin r by sin I, and from that we can get the critical angle as theta c equal to sin inverse of n2 by n1. So that will give the formula for finding out the critical angle. So another parameter which is important is the numerical aperture. So the numerical aperture will give a measure of the light gathering capacity of the optical fiber. So it is represented as Na and it is equal to n sin theta max over the nf square minus nc square. That means the root of difference between the squares of the refractive index of the core and clad. So here the refractive index, n is the refractive index of the medium. Theta max is the angle of acceptance. It is the angle between the acceptance cone and the normal. And NF is the refractive index of the fiber core, and NC is the refractive index of the core and in cladding, and NF is the refractive index of the fiber core. So the optical fiber is mainly used in fiber optic communication, fiber sensors and medical healthcare. For endoscopy and all, we are using the optical fiber only. So here it will show the attenuation coefficient of a silica glass versus wavelength. So we can see that at around 1550 is the lowest loss is possible. So that is the communication wavelength which we are using. So depending upon the wavelength, this attenuation is varying. Now we will come to the optical waveguides and couplers. So here there are different kinds of optical waveguides, different shapes are available and different kind of couplers are there. How we are coupling the light into the fiber. So all those things are different categories are there, like n-bud coupling, free space coupling, etc. So now we will see what are the different types of optical fibers. So one is the single mode fiber and another one is the multi-mode fiber. Single mode fiber is the fiber cable that is designed to carry only a single mode of light, that is the transverse mode. So in the case of mode, we can consider as the light path actually. So in the single mode fiber, there will be only single mode which is propagating along the fiber. And in the case of multi-mode, there will be different paths through which the light will be transmitted from one end to the other end. So the multi-mode will be having a higher core diameter and a single mode is having a less diameter actually. So it is very much difficult to launch the light in the single mode fiber compared to the multi-mode fiber, and the light gathering capacity will be more for the multi-mode fiber. And another classification is the step index and graded index. So this will show how the refractive index is varying from the center of the core towards the cladding side. So if the variation is a sudden variation, it is called a step index as shown in the figure. It is a rectangular function it is coming. And if it is gradually varying, it is called a graded index fiber. So this here it is showing how the step index and single mode fiber and step index, that variation, the different variations, how the light waves are traveling. Then another important parameter which is related to the fiber optics is the fiber optic cable is the V number. So another important parameter is the V number. So this V number will tell us whether the optical fiber will act as a single mode for a particular wavelength. So the V number equation is V is equal to 2 pi a by lambda into Na. So the V number depends upon the wavelength. That is obvious from the equation. So here we need to make sure that we need to understand that if the single mode fiber, if a fiber has to work as a single mode fiber for a given wavelength, then for that wavelength the V number should be less than 2.405. So if an optical fiber which will work as a single mode for a given wavelength may not work as single mode for another wavelength. Or a fiber which will act as a single mode for a given wavelength will act as a multi-mode for another wavelength. So that we need to keep in our mind. So these are the things which we need to understand about the ray optics. Thank you very much.